In July 2022, astronomers analyzing the first deep-field images from the James Webb Space Telescope discovered something that should not exist. A massive, fully formed galaxy designated Glass Z13, appearing in observations that peer back to just 300 million years after the Big Bang. But this galaxy contains hundreds of billions of stars arranged in sophisticated spiral structures with chemical compositions that require multiple generations of stellar evolution. The problem is simple and absolute. There has not been enough time in the universe for this galaxy to exist. According to every model of cosmic evolution, every simulation of early galaxy formation, every theoretical framework we've developed over a century of modern cosmology, this object is impossible. Yet there it sits in our data, undeniable and perfect, challenging the very foundation of our understanding about how the universe began. What if our most fundamental assumptions about cosmic history are wrong? What if the Big Bang timeline that we have refined through decades of observation and calculation represents not the true age of the universe, but merely the limit of our current measurement capabilities? Today we journey through discoveries that challenge everything we thought we knew about the birth and evolution of galaxies. We will examine impossible galaxies appearing too early in cosmic time, explore stars that are older than the universe itself, and investigate why our most advanced space telescope keeps finding objects that break every rule. Prepare yourselves. We begin. On December 25, 2021, the James Webb Space Telescope launched from French Guiana aboard an Ariane 5 rocket carrying humanity's most sophisticated astronomical instrument into space. The telescope travelled for 1 month to reach its operational position at the second Lagrange point, a gravitationally stable location 1.5 million kilometres from Earth, where the combined gravity of Earth and Sun keeps the telescope in a fixed position relative to both bodies. Engineers spent 6 months calibrating the 18 hexagonal beryllium mirror segments, each coated with a microscopically thin layer of gold to optimize infrared reflection. These mirrors, when properly aligned, function as a single primary mirror 6.5 meters in diameter, nearly 3 times larger than the Hubble Space Telescope's 2.4 meter primary mirror. The engineering behind James Webb represents decades of technological development. Each beryllium mirror segment weighs approximately 20 kilograms and measures 1.32 meters across flat to flat. Beryllium was chosen for its unique properties. The metal remains stable across extreme temperature variations, crucial for a telescope that operates at temperatures around -233 degrees Celsius. It possesses exceptional stiffness-to-weight ratio, providing the rigidity needed for precise optical alignment while minimizing mass for launch. The gold coating, just 100 nanometers thick, contains approximately 48.25 grams of gold per mirror segment. Gold reflects infrared light more efficiently than any other practical coating material, making it essential for the telescope's primary mission of observing in infrared wavelengths. The alignment process that transforms 18 independent mirrors into a single functional telescope demonstrates extraordinary precision. Each segment connects to the telescope structure through 6 actuators and 1 central 7th actuator. These actuators can adjust each mirror's position in 6 degrees of freedom with precision measured in nanometers. During the initial alignment phase, engineers used a specialized camera and suite of optical tools to measure the wavefront, the shape of collected light waves from each mirror segment. The measurements revealed how each mirror needed adjustment to bring all 18 into perfect alignment. This process required weeks of careful work, with engineers making minute adjustments, measuring results, and refining the corrections until all segments functioned as one optical system. The telescope carries 4 main scientific instruments, each designed to observe different aspects of the infrared universe. The near-infrared camera, or NIR cam, serves as the telescope's primary imager, capable of detecting light in wavelengths from 0.6 to 5 micrometers. It contains 10 mercury-cadmium telluride detectors, each with roughly 4 million pixels, allowing it to capture extraordinarily detailed images of distant objects. NIR cam also plays a crucial role in aligning the telescope's mirrors, using specialized optical systems to measure the wavefront from each mirror segment during the alignment process. The camera's temperature must be maintained at around -234 degrees Celsius for optimal performance, requiring it to sit behind a massive sunshield that blocks heat from the sun, earth and moon. The near-infrared spectrograph, or NIR spec, splits light into spectra, allowing astronomers to determine the chemical composition, temperature and motion of observed objects. The instrument can observe 100 objects simultaneously using an innovative microshutter array. This array contains roughly 250,000 tiny shutters, each 100 by 200 micrometers in size, that can be individually opened or closed to select which object's light passes through to the detectors. This technology allows NIR spec to obtain spectra from multiple galaxies in a single observation, dramatically increasing the telescope's efficiency for spectroscopic surveys. The instrument operates in wavelengths from 0.6 to 5.3 micrometers, overlapping with NIR cam's range, but providing the spectroscopic capability NIR cam lacks. The mid-infrared instrument called MIRI observes at longer wavelengths between 5 and 28 micrometers. These longer wavelengths allow MIRI to see even cooler objects than NIRCam or NIRSpec can detect, including very dusty regions of space and objects at extreme redshifts where the universe's expansion has stretched their light into the mid-infrared range. MIRI requires even colder operating temperatures than the near-infrared instruments, maintaining temperatures around -266 degrees Celsius, just 7 degrees above absolute zero. Achieving this extreme cold requires an additional cooling system beyond the sunshield. A cryocooler uses helium gas in a closed-loop system, compressing and expanding it to remove heat from MIRI's detectors through a purely mechanical process that requires no consumable coolant. The fine guidance sensor, while not a scientific instrument, proves essential for the telescope's operation. It precisely measures the positions of guide stars, bright reference stars that allow the telescope to maintain pointing accuracy. The sensor can detect motions of less than 7 milliseconds, roughly equivalent to detecting the width of a human hair from 24 kilometers away. This precision keeps the telescope locked onto target throughout observations lasting hours or even days, ensuring that collected photons from faint distant objects accumulate in exactly the right locations on the detectors. Without this capability, the telescope could not observe the faintest, most distant galaxies that represent its primary scientific targets. The larger mirror gives James Webb extraordinary light-gathering capability, allowing it to detect objects far fainter and more distant than any previous space telescope. But the real revolution comes from its infrared sensitivity. While Hubble operates primarily in visible and ultraviolet wavelengths, James Webb observes in infrared, detecting light with wavelengths ranging from 0.6 to 28 micrometers. This infrared capability allows the telescope to see through cosmic dust that blocks visible light and, most crucially, to observe the most distant objects in the universe whose light has been stretched into infrared wavelengths by cosmic expansion. The farther away an object is, the faster it moves away from us due to the expansion of space itself, and this motion stretches the light to longer, redder wavelengths in a phenomenon called cosmological redshift. Scientists measure this stretching using a value called redshift, denoted by the letter Z. A redshift of 0 means no stretching, indicating an object in our immediate cosmic neighbourhood. A redshift of 1 corresponds to a look-back time of about 8 billion years, when the universe was roughly 60% of its current age. Hubble routinely observed galaxies with redshifts up to Z equals 8 or 9, corresponding to look-back times of about 13 billion years, just 500 to 600 million years after the Big Bang. But James Webb was designed to push far beyond these limits, potentially observing the very first galaxies that formed in the early universe. The telescope's infrared instruments can detect galaxies with redshifts exceeding Z equals 20, corresponding to observations of the universe when it was less than 200 million years old. Understanding redshift requires grasping how cosmic expansion affects light traveling through space. When a galaxy emits light, that light consists of photons with specific wavelengths determined by the physical processes that produced them. As these photons travel through expanding space toward Earth, the expansion stretches the space between the wave crests, increasing the wavelength. The amount of stretching depends on how much the universe has expanded since the light was emitted. For nearby objects, the expansion is minimal and the wavelength shift is small. For very distant objects, the universe has expanded substantially since their light began its journey, stretching the wavelengths dramatically. A galaxy at redshift Z equals 13, like glass Z 13, emitted its light when the universe was just 300 million years old. The universe has since expanded by a factor of 14, meaning space is now 14 times larger than when that light began its journey. This expansion stretches all the wavelengths by the same factor. Consider a photon of ultraviolet light emitted by hot young stars in an early galaxy. In the galaxy's reference frame, this photon might have a wavelength of 100 nanometers, firmly in the ultraviolet range invisible to human eyes. As this photon travels through expanding space for 13.5 billion years, the cosmic expansion stretches its wavelength by a factor of 14. By the time it reaches James Webb's mirrors, the photon has a wavelength of 1,400 nanometers, placing it in the near-infrared range that NIRCam can detect. Without infrared capability, we would be blind to the most distant galaxies because their ultraviolet and visible light has been stretched beyond the range our eyes can see. This is why James Webb's infrared sensitivity is so crucial for studying the early universe. The telescope observes in precisely the wavelengths where light from the first galaxies ends up after billions of years of cosmic stretching. On July 12, 2022, NASA released the first science images from James Webb. The deep field image revealed thousands of galaxies in a tiny patch of sky, no larger than a grain of sand held at arm's length. Each point of light in this image represents an entire galaxy, containing billions or trillions of stars. Some of these galaxies appear as they were billions of years ago, their light travelling through expanding space for most of the universe's lifetime before finally reaching the telescope's detectors. But a few objects in this image appear different. They showed the characteristic colours and spectral signatures of galaxies at extreme redshifts, far beyond what Hubble could observe. Astronomers immediately began analysing these potential high redshift candidates, measuring their distances through a technique called photometric redshift estimation. This method examines how bright an object appears in different infrared wavelengths, and compares these measurements to theoretical models of how galaxies should look at various distances. The technique works because galaxies at different redshifts have distinctive spectral signatures. Young star-forming galaxies emit strongly in ultraviolet wavelengths due to hot massive stars. As redshift increases, this ultraviolet emission shifts into visible wavelengths, then infrared, then mid-infrared. By measuring a galaxy's brightness through multiple filters covering different wavelength ranges, astronomers can identify which redshift best matches the observed pattern. The results shocked the scientific community. Multiple galaxies in the deep field image appeared to have redshifts between Z equals 12 and Z equals 16, corresponding to observations of the universe when it was just 200 to 300 million years old. One particular galaxy, designated Glass Z13, showed a photometric redshift of Z equals 13.1, suggesting we were observing it as it appeared just 300 million years after the Big Bang. Follow-up observations using the telescope's spectroscopic instruments confirmed these extraordinary distances. Spectroscopy splits light into its component wavelengths, allowing astronomers to identify specific spectral features like hydrogen emission lines that serve as cosmic distance markers. When these features appear shifted to longer wavelengths, the amount of shift reveals precisely how far away the object is and how fast it is receding from us. The spectroscopic data for Glass Z13 confirmed a redshift very close to the photometric estimate, conclusively placing this galaxy in the early universe, just 300 million years after the Big Bang. But here is where the mystery deepens. The galaxy is far too massive and far too evolved to exist at this cosmic epoch. Glass Z13 has a stellar mass estimated at 1 billion solar masses, meaning it contains stars whose combined mass equals 1 billion times the mass of our Sun. This represents an enormous quantity of matter that has already been processed through nuclear fusion in stellar cores, converted from primordial hydrogen and helium into heavier elements, and assembled into stable gravitational structures. The galaxy spans roughly 1,600 light-years across, small by modern standards but remarkably well-defined for such an early cosmic time. Its light profile suggests rotating disk structure with a central bulge, indicating sophisticated gravitational organization that requires time to develop. Most troubling of all, its spectral signature reveals the presence of elements heavier than helium, including carbon, nitrogen, and oxygen. These elements can only form inside stars through nucleosynthesis, and are only released into the surrounding space when stars explode as supernovae at the end of their lives. The detection of these heavy elements demands careful analysis. When astronomers obtain a spectrum of a galaxy, they see emission and absorption lines corresponding to different chemical elements at specific wavelengths. Hydrogen produces strong emission lines in the ultraviolet when young hot stars ionize surrounding hydrogen gas. This ionized gas then recombines, with electrons cascading down through energy levels and emitting photons at characteristic wavelengths. The strongest hydrogen line, called Lyman alpha, appears at 121.6 nanometers in the rest frame. In Glass Z13, cosmic expansion shifts this line to 1,713 nanometers in the near-infrared, where NIR spec can detect it. But the spectrum also shows fainter emission lines from carbon, nitrogen, and oxygen. These heavier elements produce emission lines at longer wavelengths in the rest frame, appearing in the infrared after redshift stretching. Their presence proves that stars in this galaxy have already undergone nuclear fusion beyond the simple hydrogen to helium conversion that powers most stellar energy generation. Carbon forms inside stars through the triple alpha process, where 3 helium nuclei fuse together at temperatures exceeding 100 million degrees Celsius. This process occurs in the cores of stars massive enough to exhaust their hydrogen fuel and contract their cores until temperatures and pressures become high enough for helium fusion. Such stars must be at least somewhat massive, typically exceeding 0.8 solar masses, and the triple alpha process begins only after they have already spent millions to billions of years fusing hydrogen. Nitrogen production requires even more complex nucleosynthesis, forming primarily through the CNO cycle in massive stars, or through subsequent processing of carbon in stellar interiors. Oxygen forms through helium fusion in massive stars, where two helium nuclei fuse with a carbon nucleus to create oxygen. All these processes require time. The problem intensifies when we consider how these elements escape stellar interiors to enrich the surrounding gas. Elements produced in stellar cores remain locked inside stars until those stars die. Low-mass stars can eventually shed their outer layers as planetary nebulae, gently releasing their nuclear products into space over thousands of years. But this process occurs only when such stars reach the end of their lives, typically after billions of years of hydrogen burning. Massive stars die more dramatically as supernovae, explosively releasing their contents, including all the carbon, nitrogen, oxygen, and heavier elements produced during their lives. These explosions happen much faster, within just a few million years after the star forms, but they still require those few million years to pass. For glass Z13 to show oxygen, carbon, and nitrogen in its spectrum, enough stars must have completed their entire life cycles, from formation through nuclear fusion to explosive death, that the ejected material enriched the interstellar gas from which subsequent generations of stars formed. The problem becomes clear when we calculate how long these processes should take. The first stars in the universe, called population 3 stars, formed from purely primordial gas containing only hydrogen and helium left over from the Big Bang. Theoretical models suggest these stars were extremely massive, perhaps 100 to 300 solar masses, burning their nuclear fuel with incredible intensity, and living for only 2 to 3 million years before exploding as supernovae. These explosions seeded the surrounding space with the first heavy elements, allowing a second generation of stars to form from gas, enriched with carbon, nitrogen, oxygen, and other elements produced by the first generation. These second-generation stars, called population 2 stars, live longer and have more varied masses. Some might persist for billions of years. A third generation, population 1 stars like our Sun, forms from even more enriched material. To produce a galaxy containing 1 billion solar masses of stars, including multiple generations showing heavy element enrichment, requires hundreds of millions of years of continuous star formation. The first generation of stars must form, live their short lives, and explode. The ejected material must mix with surrounding gas and cool enough to collapse again, forming new stars. This cycle must repeat multiple times to build up the observed population and chemical enrichment. Simulations of early galaxy formation suggest this process requires at least 500 to 700 million years to produce galaxies with masses approaching 1 billion solar masses. But glass Z13 exists just 300 million years after the Big Bang. The universe has not had enough time for this galaxy to form through any known process. The enrichment timeline becomes even more constrained when we examine the specific abundances observed. The ratio of nitrogen to oxygen in glass Z13's pollen spectrum suggests substantial nitrogen production, which requires either very massive stars with strong stellar winds, or intermediate mass stars that have processed material through multiple burning stages. Both scenarios demand significant time. Similarly, the presence of certain spectral features associated with evolved stellar populations, like ionized silicon and sulfur, indicates that many stars have already reached advanced stages of nuclear burning. The abundances pattern resembles what we see in relatively metal-rich galaxies in the local universe, galaxies that have undergone billions of years of chemical evolution. Seeing similar patterns in a galaxy just 300 million years after the Big Bang suggests that early star formation and enrichment occurred far more rapidly than any theoretical model predicts. Similar problems appear throughout the James Webb Deep Field data. Astronomers have identified more than a dozen galaxy candidates with redshifts exceeding Z equals 10, corresponding to observations within the first 500 million years after the Big Bang. Many of these galaxies show masses and structural properties that seem impossible given the available time for formation. One galaxy, designated Sears 93316, appears at a photometric redshift of Z equals 16.7, corresponding to just 250 million years after the Big Bang, yet shows a stellar mass of roughly 500 million solar masses organized in a clear disk structure. Another object, designated CEERS 2_588, displays a redshift of Z equals 14.3, with evidence for active star formation producing thousands of solar masses worth of new stars every year, a rate that should deplete the available gas reservoir within just a few million years. Additional discoveries compound the mystery. Galaxy JD1 at redshift Z equals 9.1. One shows evidence for a mature stellar population with ages approaching 200 million years. If this age estimate proves correct, stars in this galaxy must have begun forming just 100 to 150 million years after the Big Bang, during or immediately following the Dark Ages, when the first stars were supposed to be forming. Galaxy MAX 0647-JD, initially discovered by Hubble but studied in detail by James Webb, appears at redshift Z equals 10.7, yet displays three distinct bright regions suggesting it might be a merging system of smaller galaxies. This would require that small proto-galaxies formed even earlier, and have now begun the merger process that builds larger structures, further compressing the timeline available for initial structure formation. Galaxy Sears 2-588, mentioned earlier, presents particularly puzzling properties. Its extremely high star formation rate, estimated at roughly 5,000 solar masses per year, exceeds the rates seen in the most active star-forming galaxies in the modern universe by factors of 100 or more. Such extreme rates can theoretically occur during galaxy mergers when clouds of gas collide and compress, triggering intense bursts of star formation. But galaxy mergers should be rare in the very early universe when galaxies are just forming, and the average distance between them remains large. The presence of such extreme star formation at redshift Z equals 14.3 suggests either that mergers occurred far more frequently than models predict, or that early galaxies could achieve extreme star formation rates through mechanisms we do not yet understand. Spectroscopic follow-up of several high redshift candidates has revealed additional surprising features. Some galaxies show evidence for extremely rapid chemical enrichment, with oxygen abundances approaching 20 to 30% of solar values despite existing less than 400 million years after the Big Bang. Solar oxygen abundance represents the result of roughly 9 billion years of stellar evolution in the Milky Way's disk, with generations of stars gradually enriching the interstellar medium with oxygen produced in supernova explosions. Seeing similar enrichment levels in galaxies 1/30th the age of the Sun's environment suggests that early enrichment proceeded at rates 30 times faster than what we observe in the modern universe. Some theoretical models have proposed that the first stars might have been more efficient at producing and ejecting heavy elements than modern stars, but even optimistic models struggle to explain enrichment this rapid. The sheer number of these massive early galaxies creates additional problems. Theoretical models of structure formation in the early universe predict that galaxies should build up gradually through a hierarchical process. Small clumps of dark matter collapse first, forming gravitational wells that attract ordinary matter. Gas falls into these dark matter halos, cools, and fragments to form the first stars. These small proto-galaxies then merge over hundreds of millions of years to form progressively larger systems. The models predict that galaxies with masses exceeding 1 billion solar masses should be extremely rare in the first 500 million years after the Big Bang, with perhaps only a handful existing in the entire observable universe at that epoch. This hierarchical model of structure formation rests on decades of theoretical work and computer simulations. The process begins with tiny density fluctuations in the early universe, variations of perhaps 1 part in 100,000 in the distribution of matter. These fluctuations, imprinted during the inflationary epoch in the first fraction of a second after the Big Bang, serve as the seeds for all future structure. Observations of the cosmic microwave background radiation, the faint glow left over from 380,000 years after the Big Bang, reveal these primordial density fluctuations frozen in the temperature patterns across the sky. Regions that were slightly denser than average show up as slightly warmer spots in the cosmic microwave background, while less dense regions appear slightly cooler. These temperature variations are tiny, just a few tens of microkelvins against a background temperature of 2.7 Kelvin, but they mark the locations where structure will eventually form. Dark matter, which does not interact with light or ordinary matter except through gravity, begins collapsing into halos wherever these density enhancements exist. Unlike ordinary matter, dark matter does not radiate energy or experience pressure forces that resist collapse. It simply responds to gravity, falling inwards toward regions of higher density. As dark matter accumulates, its gravitational pull strengthens, attracting more dark matter and also pulling in ordinary matter, the hydrogen and helium gas that will eventually form stars. The first dark matter halos to form are small, perhaps containing only millions of solar masses worth of dark matter, but they represent the first gravitationally bound structures in the universe, tiny islands of condensed matter in an otherwise nearly uniform expanding cosmos. Ordinary matter falls into these dark matter halos and begins its own collapse. Initially, the gas remains hot, heated by the energy released as it falls inward into the gravitational potential well of the dark matter halo. For stars to form, this gas must cool enough that its thermal pressure can no longer support it against further gravitational collapse. In the very early universe, before stars have produced any heavy elements, the only available cooling mechanisms involve hydrogen and helium. Hydrogen atoms can cool gas through electronic transitions, with electrons jumping between energy levels and radiating away energy as photons. But this process only works if neutral hydrogen atoms exist. In the first 100 million years after the Big Bang, the universe remains mostly neutral, filled with hydrogen and helium atoms. As gas falls into dark matter halos, it heats up from gravitational compression, but can cool through hydrogen line radiation, allowing it to continue collapsing to form the first stars. These first stars change everything. Their ultraviolet radiation begins ionizing the surrounding hydrogen gas, creating bubbles of ionized material that grow over time. Their supernova explosions inject energy and newly created heavy elements into the surrounding gas. This feedback can either promote further star formation by compressing nearby gas clouds, or suppress it by heating gas and making it harder to collapse. The complex interplay between gravity trying to collapse gas into stars and feedback processes trying to prevent this collapse determines how efficiently galaxies form and grow. Current models suggest that feedback processes are quite efficient at regulating star formation, allowing only a few % of available gas to convert into stars before feedback blows the remaining gas away or heats it too much to continue forming stars. As time progresses, the small protogalaxies begin to merge. Two dark matter halos gravitationally attract each other, spiral inward, and eventually combine into a single larger halo. The gas and stars in each protogalaxy also merge, though the process can be violent, triggering intense bursts of star formation as gas clouds collide and compress. Through countless such mergers over hundreds of millions of years, the small building blocks gradually assemble into larger galaxies. This bottom-up assembly process, where small structures form first and merge to build larger ones, represents the core prediction of hierarchical structure formation models. The models successfully reproduce many properties of the modern universe, matching observations of galaxy clustering, the sizes and shapes of cosmic voids and superclusters, and the statistical properties of the galaxy distribution. They predict that very massive galaxies should be rare at early times because not enough time has passed for sufficient mergers to occur. James Webb observations suggest otherwise. The telescope finds massive galaxies at high redshifts at rates roughly 10 to 100 times higher than theoretical predictions. Extrapolating from the small areas surveyed so far suggests that thousands or even tens of thousands of massive galaxies might exist in the early universe, far exceeding what our models predict. This discrepancy has profound implications. Either our models of galaxy formation are fundamentally wrong, requiring major revisions to incorporate new physics we don't currently understand, or our interpretation of the observations is flawed in ways that make distant galaxies appear more massive or numerous than they actually are. Consider what the observations demand. If glass E13 really exists at redshift z equals 13.1 with a mass of 1 billion solar masses, then star formation must have begun extremely early, perhaps within 50 to 100 million years after the Big Bang, and proceeded at rates far exceeding what theoretical models consider possible. The efficiency of converting gas into stars would need to approach 100%, meaning essentially all available gas in the early protogalaxy collapsed to form stars within the first few 100 million years. This contradicts everything we know about star formation in the modern universe, where only a few % of available gas typically converts into stars before stellar feedback processes like radiation pressure and supernova explosions blow the remaining gas away and halt further star formation. One possibility involves the nature of dark matter itself. The standard cosmological model assumes dark matter consists of cold dark matter particles, meaning particles that move slowly compared to the speed of light and clump together efficiently under gravity. This cold dark matter model successfully explains the large-scale structure of the universe and the properties of galaxies in the modern cosmos. But perhaps dark matter behaves differently in the very early universe. If dark matter particles possess properties we have not yet characterized, or if there are additional components to dark matter that become important only at high densities or early times, this could affect how quickly structure forms. Dark matter that clumps more efficiently in the early universe than our models predict could accelerate galaxy formation, providing more and deeper gravitational potential wells for gas to fall into. This would allow earlier and more rapid star formation, potentially explaining the observed abundance of massive early galaxies. Alternatively, the physics of star formation itself might differ in the early universe. Our theoretical models of star formation make assumptions about how gas cools, fragments, and collapses to form stars. These assumptions work well for explaining star formation in the modern universe, but perhaps conditions in the early universe were different enough that our models fail. The first stars formed from purely primordial gas, without any heavy elements to help cool the gas and enable fragmentation into smaller clumps. Theoretical models suggest this resulted in very massive stars, hundreds of times more massive than typical stars today. But what if our models of population 3 star formation are incomplete? If the first stars could form more efficiently than we think, or if they converted a larger fraction of available gas into stars, this could help explain the rapid buildup of stellar mass in early galaxies. The chemical enrichment problem is perhaps even more severe. The presence of heavy elements in Glass 13's spectrum indicates that multiple generations of stars have already lived and died by the time we observe this galaxy. The first generation of pristine population 3 stars formed from primordial gas, burned for 2 to 3 million years, and exploded as supernova. Their ejecta mix with surrounding gas to form a second generation of stars. Some of these second generation stars were massive enough to also burn quickly and explode, further enriching the gas. This cycle continued until the galaxy accumulated enough stars and heavy elements to match observations. Each cycle requires time for stars to form, evolve, explode, and for the ejecta to mix and cool before the next generation can form. Adding up these timescales suggests a minimum of 200 to 300 million years for the observed enrichment, leaving only a few tens of millions of years between the Big Bang and the start of star formation in Glass Z13. The mixing timescale deserves particular attention. When a massive star explodes as a supernova, it ejects several solar masses of material at velocities approaching 10,000 kilometers per second. This material, enriched with heavy elements produced during the star's life and in the explosion itself, expands outward as a bubble of hot gas and plasma. Initially, this ejecta forms a distinct shell expanding through the surrounding interstellar medium. Over time, the expanding shell slows as it sweeps up more and more ambient gas. Eventually, it stalls and begins to mix with the surrounding material through turbulent processes. Only after this mixing can the enriched material participate in forming new stars. The mixing process requires tens of millions of years in modern galaxies, possibly longer in the early universe where conditions differ. Each generation of stars thus requires not just the time for stellar evolution, but also substantial additional time for the mixing and cooling of ejecta before the next generation can form. Some researchers have proposed that mixing might proceed faster in the early universe than in modern galaxies. The early universe has lower average densities, and dark matter halos are less massive on average. This could allow supernova ejecta to escape more easily from protogalaxies, preventing heavy elements from becoming available for subsequent star formation. But observations show heavy element enrichment, indicating that at least some ejecta remained bound to the protogalaxy and mixed with the gas reservoir. Theoretical work suggests that low-mass halos would struggle to retain supernova ejecta, while more massive halos would have deeper gravitational potential wells that keep ejecta bound. The massive early galaxies like Glass Z13 fall into the latter category, implying they should retain ejecta and undergo multiple generations of star formation. But this makes the timeline problem even more severe because now we must explain how such massive dark matter halos assembled so quickly. But the Big Bang model posits that the first 100 million years after the beginning were a dark age when no stars existed at all. The universe expanded and cooled from its initial hot, dense state. For the first 380,000 years, matter existed as a hot plasma of electrons, protons, and helium nuclei, too energetic for atoms to form. Photons scattered continuously off the free electrons, making the universe opaque like a thick fog. This is the epoch of the cosmic microwave background. the remnant radiation we detect today as a faint microwave glow filling all of space. When the universe cooled enough for electrons and nuclei to combine into neutral atoms, the fog cleared and photons could travel freely. This moment, called recombination, ended the plasma era and began the Dark Ages. During the Dark Ages, the universe contained only neutral hydrogen and helium gas, slowly collapsing into structures under the influence of gravity and dark matter. No stars existed yet because the gas had not reached sufficient densities and temperatures to trigger nuclear fusion. The Dark Ages lasted until the first stars ignited, producing radiation that began to reionize the hydrogen gas by breaking atoms back apart into electrons and protons. This epoch of reionization probably began around 100 to 200 million years after the Big Bang, and continued for several hundred million years until most of the neutral hydrogen in the universe had been ionized. The presence of massive evolved galaxies like Glass D13 at 300 million years suggests that star formation must have begun very early in this timeline, perhaps 50 to 100 million years after the Big Bang, giving only 200 to 250 million years for all subsequent evolution. The epoch of reionization provides independent constraints on when the first stars formed. Observations of distant quasars at redshifts around Z = 6 to 7 show that the intergalactic medium was largely ionized by that epoch, roughly 1 billion years after the Big Bang. This means reionization must have been mostly complete by then. Working backward, if reionization took several hundred million years, it must have begun by redshift Z = 10 to 15, corresponding to 200 to 400 million years after the Big Bang. This timeline requires the first stars to have formed even earlier, perhaps at redshifts approaching Z = 20 or beyond. The discovery of massive galaxies at Z = 13 to 16 fits within this timeline, but barely. And the masses and chemical enrichment suggest these galaxies formed from proto-galactic structures that must have begun collapsing even earlier. Some scientists have proposed alternative explanations for these observations. Perhaps our distance measurements are wrong, and these galaxies are not as far away as we think. Photometric redshift estimates can sometimes be fooled by unusual spectral features or dust absorption that mimics the signature of extreme distance. Maybe Glass D13 is actually a lower redshift galaxy at Z = 5 or Z = 6, corresponding to 1 to 1.5 billion years after the Big Bang, with some peculiar property that makes its light appear as if it came from much farther away. But spectroscopic follow-up observations have confirmed the high redshifts for several of these objects, making systematic errors in distance measurements increasingly unlikely. The spectroscopic technique identifies specific atomic transitions like hydrogen Lyman alpha emission that occur at precise known wavelengths. The observed wavelengths of these features determine the redshift directly, independent of assumptions about stellar populations or galaxy properties. Perhaps our mass estimates are wrong. Measuring the stellar mass of a distant galaxy requires complex modelling of how stars of different ages and compositions contribute to the total light we observe. If we have misestimated the mass-to-light ratio, the true stellar masses might be lower than calculated. But even reducing the mass estimates by factors of 2 or 3 does not resolve the tension with theoretical models. The galaxies would still be too massive for their observed epochs. Moreover, independent evidence from gravitational lensing studies, which measure mass directly from gravitational effects without relying on light from stars, confirms that at least some early galaxies have substantial masses approaching those estimated from stellar population modelling. Gravitational lensing occurs when light from a distant background object passes near a massive foreground object. The foreground object's gravity bends space-time, deflecting the light rays and magnifying the background object. The amount of magnification depends on the total mass of the foreground lens, including both visible matter and dark matter. Lensing observations of some high redshift galaxies show magnification patterns consistent with the mass estimates derived from stellar population analysis. Perhaps the star formation history was extremely unusual in these early galaxies, with brief intense bursts that produced enormous numbers of stars very rapidly before shutting down. But this explanation struggles to account for the observed chemical enrichment patterns and structural properties. Brief starbursts should produce galaxies with simple structures and limited chemical evolution, not the organized disks and multiple stellar populations we observe. Furthermore, theoretical models of what triggers starbursts in galaxies require specific conditions like galaxy mergers or interactions with other systems, mechanisms that should be rare in the very early universe when galaxies are widely separated and structure is just beginning to form. The average distance between galaxies at redshift z equals 13 is many millions of light years, making encounters infrequent. Even if mergers did occur, they would need to happen at precisely the right time to produce the observed properties, adding another layer of fine-tuning that seems unlikely. The evidence from other James Webb observations compounds the mystery. In August 2022, astronomers announced the discovery of galaxy candidate Sears 93316 at a photometric redshift of Z equals 16.7. If confirmed, this would make it one of the most distant objects ever observed, appearing as it was just 250 million years after the Big Bang. The galaxy shows characteristics suggesting substantial star formation and mass assembly have already occurred. Its spectrum contains emission lines from oxygen, a heavy element that can only form in stars, indicating that at least 2 or 3 generations of stars have already lived and died by this extraordinarily early time. The oxygen abundance appears relatively high, approaching 10 to 15% of solar values, suggesting rapid and efficient enrichment. Such high oxygen abundances typically require tens or hundreds of supernova explosions to achieve, each contributing oxygen produced through helium fusion in massive stellar cores. In October 2022, researchers analyzing James Webb spectroscopic data announced the discovery of massive black holes in several early galaxies at redshifts between Z equals 10 and Z equals 12. These supermassive black holes, each containing millions or even billions of solar masses, sit at the centers of their host galaxies and power extremely luminous emissions as surrounding gas falls inward and heats to millions of degrees. The existence of supermassive black holes at such early times creates its own set of problems for theoretical models. Black holes are thought to form from the collapse of massive stars, beginning with masses of perhaps 100 solar masses. These seed black holes then grow by accreting surrounding gas and merging with other black holes. But growing a supermassive black hole containing billions of solar masses requires hundreds of millions of years of continuous accretion, even under idealized conditions. Finding such objects at redshifts of Z equals 10 or higher, corresponding to less than 500 million years after the Big Bang, suggests that either the seed black holes must have been far more massive than theory predicts, or the growth rates must have been far faster than models allow. The standard model of supermassive black hole growth assumes that seed black holes form from the first generation of massive stars, perhaps through direct collapse of the stellar core after nuclear fuel is exhausted. These seeds might contain 50 to 150 solar masses initially. They then grow primarily through gas accretion, pulling in matter from their surroundings. As gas spirals inward toward the black hole, it forms an accretion disk, a rotating structure where gravitational energy converts into heat through friction and tidal forces. The accretion disk becomes extremely hot, radiating enormous amounts of energy across the electromagnetic spectrum. This radiation exerts outward pressure on surrounding gas, potentially halting further accretion when the radiation pressure balances the inward gravitational pull. This balance defines the Eddington limit, the maximum luminosity a steadily accreting black hole can achieve. At the Eddington limit, growth proceeds at a relatively sedate rate, with the black hole roughly doubling its mass every 50 million years. Starting from a 100 solar mass seed, this growth rate produces a black hole of roughly 10 million solar masses after 350 million years of continuous Eddington-limited accretion. Some early supermassive black holes exceed this mass by factors of 100, requiring either much more massive seeds or prolonged periods of super-Eddington accretion. Alternative scenarios propose that supermassive black holes could form through direct collapse of massive gas clouds in the early universe, bypassing the stellar phase entirely. If conditions are right, a cloud of primordial gas containing 100,000 or more solar masses might collapse directly into a black hole without fragmenting into stars. This would produce a much more massive seed, perhaps 100,000 solar masses, providing a head start on growth towards supermassive status. But direct collapse requires very specific conditions. The gas must be metal-free, heated to prevent fragmentation, and shielded from ultraviolet radiation that would break it apart into smaller clumps. These conditions may have existed in rare locations in the early universe, but whether they occurred frequently enough to explain all the observed supermassive black holes at high redshift remains unclear. Moreover, recent observations of multiple supermassive black holes at Z equals 10 to 13 suggest that if direct collapse did occur, it must have been relatively common, challenging models that predict it should be rare. The black hole puzzle connects to the galaxy formation problem. Supermassive black holes and their host galaxies appear to evolve together in the modern universe, with the black hole mass correlating tightly with properties of the galactic bulge like stellar mass and velocity dispersion. This correlation suggests that black hole growth and galaxy formation are intimately linked through feedback processes. As gas falls into the black hole, it releases enormous energy that heats the surrounding gas and can regulate star formation in the galaxy. The correlation between black hole mass and bulge properties extends across 4 orders of magnitude in black hole mass, from millions to tens of billions of solar masses, suggesting a fundamental physical connection rather than coincidence. Finding this relationship already established in galaxies at redshift Z equals 10 or 12 implies that both the black holes and the galaxies have already undergone substantial evolution by these early times, further compressing the available time for formation and growth. James Webb observations have also revealed unexpected properties in slightly lower redshift galaxies from epochs roughly 1 to 2 billion years after the Big Bang. Galaxies at these intermediate redshifts corresponding to Z equals 5 to Z equals 8 show structures and morphologies that appear surprisingly mature and well organized. Many display clear spiral arms, bars and other features that were thought to develop only after several billion years of gravitational evolution. The presence of these structures so early suggests that gravitational instabilities and dynamical processes organize galaxies much faster than previously believed. Spiral arms, those beautiful curved structures we see in galaxies like the Milky Way and Andromeda, form through density wave instabilities in rotating galactic disks. Gravitational perturbations create regions of enhanced density that orbit the galactic center at different speeds than the underlying stars and gas. These waves compress gas as they pass through, triggering star formation that lights up the spiral arms in brilliant blue and white as newly formed massive stars emit intense ultraviolet radiation. But developing stable spiral patterns requires a well-organized rotating disk with specific mass distributions and angular momentum profiles. Theoretical models suggested this level of organization should take several billion years to develop as galaxies settle down from their chaotic formation process. Fresh from mergers and still accreting gas from their surroundings, early galaxies were expected to look disturbed and irregular, not settled into elegant spiral patterns. Finding well-defined spiral structures at redshift Z equals 6 or 7, less than 1 billion years after the Big Bang, challenges these timescales. Either disks settle down faster than models predict, or spiral structures can form in systems that have not yet achieved full dynamical equilibrium. Bar structures present a similar puzzle. Galactic bars are elongated distributions of stars and gas that rotate as solid bodies through the central regions of disk galaxies. About 2/3 of spiral galaxies in the local universe possess bars, including the Milky Way. Bars form through gravitational instabilities in galactic disks, where the self-gravity of the disk enhances certain patterns of perturbation. Once formed, bars funnel gas toward the galactic center, triggering central star formation and feeding central black holes. The formation of bars requires that the disk achieve sufficient surface density and gravitational self-interaction while maintaining dynamical coherence. Theoretical models suggested bars should develop only in galaxies that have settled into stable disk configurations, requiring several billion years. But James Webb has revealed barred galaxies at redshifts exceeding Z equals 5, when the universe was less than 1.2 billion years old. The existence of these early bars suggests that disk galaxies achieved dynamical maturity far earlier than anticipated. The mystery extends beyond individual galaxies to the large-scale structure of the universe itself. Cosmological simulations that model the evolution of structure from the Big Bang to the present day predict specific patterns in how galaxies cluster and distribute throughout space. These simulations start with the initial density fluctuations measured in the cosmic microwave background, the faint variations in temperature across the sky that represent the seeds of all future structure. The simulations evolve these seeds forward in time using the laws of gravity and hydrodynamics, following how dark matter collapses into halos and how ordinary matter falls into these halos to form galaxies. The simulations successfully reproduce many properties of the modern universe, matching observations of galaxy clustering, the sizes and shapes of cosmic voids and superclusters, and the statistical properties of the galaxy distribution. But when James Webb looks at the high redshift universe, the observed distribution of massive galaxies appears to differ from simulation predictions. The massive galaxies seem more numerous and more clustered than models predict for such early times. Statistical analyses of the spatial distribution of high redshift galaxies in James Webb surveys show that massive galaxies cluster more strongly than simulations predict, suggesting they reside in dark matter halos more massive than expected. This clustering signal provides independent evidence that structure formation proceeded faster or more efficiently in the early universe than standard models allow. If dark matter halos grew more massive more quickly, this would provide stronger gravitational potential wells for gas to fall into, potentially enabling faster galaxy growth. But accelerating halo growth requires either changing the initial conditions, modifying the properties of dark matter, or invoking new physics that affect structure formation at early times. This discrepancy might indicate problems with our cosmological model, suggesting that we have misunderstood something fundamental about how structure forms in the early universe. The standard cosmological model, often called lambda CDM, includes several key components. Lambda represents the cosmological constant or dark energy. a mysterious component that drives the accelerating expansion of the universe. CDM stands for cold dark matter, the dominant form of matter that provides the gravitational scaffolding for structure formation. The model also includes ordinary matter, radiation, and neutrinos in carefully calibrated proportions determined by observations of the cosmic microwave background and other cosmological probes. Lambda CDM successfully explains a wide range of observations across cosmic time, from the Big Bang nucleosynthesis predictions of light element abundances to the detailed patterns in the cosmic microwave background to the distribution of galaxies in the modern universe. But the James Webb observations of massive early galaxies sit uncomfortably within Lambda CDM. If the observations are correct and these galaxies really are as massive as they appear at the redshifts claimed, then either Lambda CDM needs modification, or our understanding of how matter converts into stars needs dramatic revision. Some researchers have proposed modifications to dark energy behavior in the early universe. If dark energy was weaker, or had different properties in the first billion years, this could have affected the expansion rate in ways that alter the relationship between redshift and cosmic time. A slower expansion rate in the early universe would provide more time for structure to form at a given redshift, potentially allowing galaxies to grow more massive. But modifying dark energy to solve the massive early galaxy problem without breaking Lambda CDM's other successes proves challenging. One possibility involves the nature of dark matter itself. The standard model assumes dark matter consists of cold dark matter particles, meaning particles that move slowly compared to the speed of light and clump together efficiently under gravity. This cold dark matter model successfully explains the large-scale structure of the universe and the properties of galaxies in the modern cosmos. But perhaps dark matter behaves differently in the very early universe. Or perhaps there are additional components to dark matter that we have not accounted for in our models. If dark matter clumped more efficiently in the early universe than our models predict, this could accelerate galaxy formation and help explain the observed abundance of massive early galaxies. Possible mechanisms include dark matter particles that interact weakly with themselves through forces other than gravity, creating dark matter density enhancements that grow faster than pure cold dark matter predictions. Another possibility involves the physics of star formation itself. Our theoretical models of star formation make assumptions about how gas cools, fragments, and collapses to form stars. These assumptions work well for explaining star formation in the modern universe, but perhaps conditions in the early universe were different enough that our models fail. If the first stars formed more efficiently than we think, converting a larger fraction of available gas into stars in shorter time periods, this could help explain the rapid buildup of stellar mass in early galaxies. But changing star formation efficiency affects many other observable properties of galaxies, and we must ensure that any modifications to explain James Webb's early massive galaxies do not break the good agreement between models and observations in the later universe. A more radical possibility questions the Big Bang timeline itself. What if the universe is actually older than we think? The current age estimate of 13.8 billion years comes from multiple independent measurements that all converge on similar values. We measure the expansion rate of the universe, called the Hubble constant, by observing how fast distant galaxies move away from us. We measure the geometry and composition of the universe through detailed analysis of the cosmic microwave background. We measure the ages of the oldest stars in our galaxy through stellar evolution modeling. All these measurements point to an age around 13.7 to 13.8 billion years. But what if systematic errors affect all these measurements in similar ways? What if the universe is actually 15 or 16 billion years old, providing an additional 1 to 2 billion years for early galaxies to form and evolve? Such a revision would require explaining why multiple independent measurement techniques all produce similarly wrong results. It would require rethinking our understanding of cosmic expansion history, the physics of the cosmic microwave background, and stellar evolution. The required changes would be profound and would affect many areas of astrophysics beyond just early galaxy formation. The cosmic microwave background provides particularly strong constraints on the universe's age and composition, because the detailed patterns in the temperature fluctuations depend sensitively on cosmological parameters. Changing the age significantly while maintaining agreement with cosmic microwave background observations requires compensating changes to other parameters like the matter density, dark energy density, and Hubble constant. These compensating changes must maintain agreement with many other independent observations, severely constraining how much flexibility exists in the cosmological model. Scientists are reluctant to abandon a theoretical framework that successfully explains so many observations unless absolutely necessary. Lambda CDM has proven remarkably successful across a wide range of observational tests. It correctly predicts the abundances of light elements formed in Big Bang nucleosynthesis, matches the detailed statistical properties of cosmic microwave background fluctuations, explains the large-scale distribution of galaxies and dark matter, accounts for the accelerating expansion of the universe, and successfully describes the formation and evolution of cosmic structure across most of cosmic history. Modifying or replacing Lambda CDM to accommodate massive early galaxies would require explaining all these other successes while also accounting for the James Webb observations. But the James Webb discoveries may be forcing us toward precisely such a revolution in our thinking. The tension between observations and theory goes beyond just the age and mass of early galaxies. The telescope has also discovered anomalous chemical abundances in some early galaxies that challenge our understanding of stellar nucleosynthesis. The relative abundances of elements like carbon, nitrogen, oxygen, magnesium, silicon, and iron in a galaxy reflect the cumulative history of star formation and evolution in that system. Different types of stars produce different elements during their lives and deaths. Massive stars produce large amounts of oxygen and magnesium through core nuclear fusion. Intermediate mass stars produce significant carbon and nitrogen through various nucleosynthesis pathways. Type Ia supernovae, caused by exploding white dwarfs in binary systems, produce most of the iron in the universe through explosive silicon burning in the detonating star. By measuring the relative abundances of these elements in a distant galaxy, astronomers can reconstruct the star formation history and infer what types of stars have contributed to the chemical enrichment. Several of the early galaxies observed by James Webb show unusual abundance patterns that don't match standard predictions. Some show excess nitrogen relative to oxygen, suggesting an unusually high contribution from intermediate mass stars or very massive stars with strong stellar winds. Others show unexpectedly high iron abundances given their overall heavy element content, suggesting either an unusual number of type Ia supernovae or perhaps a different production mechanism for iron that operates in the early universe. These chemical anomalies might indicate that the initial mass function, the distribution of stellar masses at birth, was different in the early universe than in modern times. Theory suggests that the first stars were extremely massive, perhaps averaging 100 to 200 solar masses, because the primordial gas lacked heavy elements that help gas cool and fragment into smaller clumps during star formation. These massive stars would produce different chemical signatures than the more typical stellar populations we observe locally. But as heavy elements accumulate through successive generations, the average stellar mass should decrease toward values similar to what we observe today. The chemical anomalies in some James Webb galaxies suggest this transition might have been more complex than theoretical models predict, possibly involving an extended period where stellar masses remained higher than modern values, or where star formation proceeded through unusual pathways that produced atypical elemental abundances. The mystery deepens when we consider observations of individual stars in these early galaxies. While we cannot resolve individual stars in galaxies at redshift z equals 10 or 12 with current technology, gravitational lensing sometimes magnifies background galaxies by factors of 10 or 100, allowing us to study smaller-scale structures. In March 2023, astronomers announced the detection of individual star clusters in a galaxy at redshift z equals 6.2 that had been magnified by a foreground galaxy cluster acting as a gravitational lens. These star clusters, each containing thousands to millions of stars, show properties suggesting they formed in intense bursts of star formation lasting just a few million years. The clusters have masses of several million solar masses, making them comparable to the largest globular clusters in the Milky Way. But they formed less than 1 billion years after the Big Bang, far earlier than models predicted such massive star clusters should exist. Globular clusters are among the oldest structures in the modern universe, with ages typically exceeding 10 to 12 billion years. They contain some of the oldest stars known, with very low abundances of heavy elements indicating they formed when the universe was young. The chemical composition of globular cluster stars provides clues about the environment in which they formed, with the most metal-poor clusters likely forming from gas that had experienced very few previous generations of stars. But even the oldest globular clusters in the Milky Way appear to have formed roughly 1 to 2 billion years after the Big Bang, not in the first billion years. Finding comparable systems already existing at redshift z equals 6.2 suggests that massive star cluster formation began extremely early and proceeded very rapidly in the early universe. The discovery of these early massive star clusters connects to broader questions about how different components of galaxies assembled. Galaxies consist of multiple components: a disk of gas and stars rotating in a plane, a central bulge of older stars with random orbital motions, and a halo of old stars and globular clusters surrounding the system. In the Milky Way, these components have different ages, chemical compositions, and kinematics, suggesting they form through different processes at different times. The disk formed relatively recently through the collapse of gas into a rotating plane. The bulge likely formed earlier through a combination of gas accretion and merger events. The halo contains the oldest stars and formed through the accretion of smaller satellite galaxies over billions of years. Understanding when and how these components assembled in the early universe would shed light on galaxy formation processes. James Webb observations suggest that at least some components of galaxies assembled remarkably early. The detection of massive star clusters at redshift z equals 6.2 implies that halo-like structures existed when the universe was less than 1 billion years old. The presence of bulges and disks in galaxies at similar redshifts suggests that these components also formed early. This early assembly timeline challenges models that predicted a more gradual build-up of galactic components over several billion years. If most galactic components formed within the first billion years, this compressed timeline requires extremely rapid gas accretion and star formation that our current models struggle to explain. The cumulative weight of these observations forces a troubling conclusion. Either we have fundamentally misunderstood galaxy formation and evolution, requiring major revisions to theories that have successfully explained decades of observations in the modern universe, or we have misunderstood something even more fundamental about cosmology itself. Perhaps our interpretation of redshift as a direct measure of distance and look-back time breaks down at extreme distances. Perhaps the expansion history of the universe was different than we think. Perhaps the Big Bang model itself requires modification or exists within a broader framework we have yet to discover. Scientists have proposed several speculative ideas to resolve these tensions. Some suggest that the dark energy driving cosmic acceleration today was stronger or had different properties in the early universe. Modified dark energy behavior could have affected the expansion rate in ways that alter the relationship between redshift and cosmic time, potentially making the universe older at a given redshift than standard models predict. If dark energy was more dominant in the early universe, it would have accelerated expansion more strongly, causing structure to form earlier than in the standard model. But dark energy appears to be a cosmological constant based on its observed properties in the modern universe, showing no evidence for evolution or variation. Modifying its early behavior without contradicting current observations proves challenging. Others propose modifications to gravity itself on cosmological scales, suggesting that Einstein's general relativity might need adjustments when applied to the very early universe or to extremely large scales. Modified gravity theories can alter structure formation timescales by changing how matter clusters under gravity's influence. If gravity was stronger in the early universe than general relativity predicts, this could accelerate the collapse of matter into halos and galaxies. Various modified gravity theories have been proposed over the decades, but most have been ruled out or tightly constrained by observations of galaxy rotation curves, gravitational lensing, and the cosmic microwave background. Remaining viable theories face the challenge of explaining massive early galaxies without breaking general relativity's many observational successes. A few researchers have even questioned whether the Big Bang model accurately describes the origin of the universe. Perhaps the universe did not begin from a singular initial state 13.8 billion years ago, but instead went through a previous cycle of expansion and contraction, or emerged from some pre-existing state we have not yet characterized. Cyclic cosmological models propose that the universe undergoes infinite cycles of expansion, contraction, bounce, and re-expansion, with each cycle potentially lasting trillions of years. In these models, our observable universe represents just one phase of an eternal cosmic cycle. If the previous cycle left behind structures or density enhancements that seeded structure formation in our current cycle, this could explain how massive galaxies appeared so early. But cyclic models face severe theoretical challenges, particularly in explaining how the universe avoids accumulating disorder through infinite cycles and how physical laws remain consistent across cycle boundaries. These ideas venture far beyond mainstream cosmology and face significant theoretical challenges. But the James Webb observations may force us to consider even very speculative ideas if conventional explanations continue to fail. The scientific community remains divided on how to interpret these findings. Some astronomers argue that the observations will eventually be explained through refinements to galaxy formation models without requiring major changes to the cosmological framework. They point out that early results from new telescopes often produce surprising findings that later turn out to result from observational uncertainties or incomplete analysis. Perhaps systematic errors in photometric redshift estimates have caused some galaxies to appear more distant than they really are. Perhaps dust absorption affects the observations in ways we have not fully accounted for. Perhaps the stellar mass estimates rely on assumptions about stellar populations that break down in the early universe. Other astronomers believe the observations represent genuine challenges to theoretical predictions that will require significant modifications to our models. They argue that the sheer number of problematic observations, the consistency across multiple independent studies, and the spectroscopic confirmation of high redshifts for several galaxies all suggest the findings are robust and not easily explained away through measurement uncertainties. These researchers advocate for serious reconsideration of galaxy formation theory, possibly including new physics that operates in the early universe but becomes less important at later times. A smaller but vocal group suggests that the observations might indicate more fundamental problems with cosmology. They point to other tensions in cosmological measurements, like the discrepancy between different determinations of the Hubble constant, as evidence that our cosmological model faces multiple challenges that might stem from a common underlying problem. The Hubble constant tension refers to the disagreement between measurements of the universe's current expansion rate derived from cosmic microwave background observations and those derived from observations of nearby supernovae and other distance indicators. The two methods give values differing by about 10%, well beyond measurement uncertainties. This tension has persisted despite years of effort to resolve it, suggesting either systematic errors in one or both measurement techniques or genuine problems with the lambda CDM model. They argue for open-minded exploration of alternative cosmological frameworks, even if these alternatives currently lack the observational support and theoretical sophistication of the standard Big Bang model. Some propose that both the massive early galaxy problem and the Hubble tension might be resolved by the modifications to dark energy or dark matter that we have not yet considered. Others suggest that the problems point toward a need for new physics beyond the standard model of particle physics that could affect both cosmological evolution and structure formation. The challenge lies in developing alternatives that explain the puzzling observations while maintaining agreement with the many observations that lambda CDM successfully explains. The debate highlights how transformative observational discoveries can upend established scientific frameworks. History provides many examples of observations that initially seemed impossible or contradictory, but ultimately led to revolutionary advances in understanding. When Galileo observed moons orbiting Jupiter in 1610, this contradicted the prevailing geocentric model of the universe that placed Earth at the centre with everything orbiting around it. The observation of Jovian moons demonstrated that not everything orbited Earth, forcing a major revision to cosmological thinking and helping establish the heliocentric model. When Edwin Hubble discovered that the universe was expanding in 1929, by observing that distant galaxies' redshifts correlated with their distances, this overturned the static universe model that even Einstein had initially favoured. Einstein had introduced the cosmological constant specifically to maintain a static universe, but Hubble's observations forced its abandonment. Ironically, the cosmological constant was later reintroduced to explain the universe's accelerating expansion. When astronomers discovered the accelerating expansion of the universe in 1998 through observations of distant type Ia supernovae, this required introducing dark energy, a completely new component to the cosmic inventory that now dominates the universe's energy budget. Prior to 1998, most cosmologists believed the universe's expansion was slowing due to gravitational attraction between galaxies and dark matter. The discovery that expansion was actually accelerating came as a complete surprise, forcing a major revision to our understanding of cosmic dynamics and the ultimate fate of the universe. The James Webb discoveries might represent a similar turning point in our understanding of the cosmos, though which direction that turn takes remains unclear. We stand at the beginning of what promises to be a golden age of infrared astronomy, with James Webb expected to operate for at least 10 to 20 years, continuously producing observations that probe ever deeper into cosmic history. Each new observation has the potential to either strengthen or further challenge our theoretical models. The coming years will reveal whether the current tensions between theory and observation can be resolved through refinements to existing models, or whether we must embrace a more revolutionary reassessment of how galaxies form and evolve in the early universe. The pace of discovery shows no signs of slowing. As of late 2023, James Webb has observed thousands of galaxies across a wide range of redshifts, and astronomers have barely begun to analyze all the available data. Each month brings new papers announcing additional massive early galaxies, unusual morphologies, anomalous chemical abundances, and unexpected types of objects. The telescope has exceeded its design specifications in terms of sensitivity and image quality, allowing observations of even fainter and more distant objects than originally planned. Planned observations over the next several years will target specific regions of the sky with exceptionally deep exposures, potentially revealing galaxies at redshifts of Z = 20 or higher, corresponding to observations within the first 200 million years after the Big Bang. These future observations might reveal whether the high redshift universe contains even more surprises, or whether the current tensions between theory and observation begin to resolve as we accumulate more data and refine our analysis techniques. Some astronomers hope that improved understanding of how dust affects observations of high redshift galaxies will reduce the apparent discrepancies between predicted and observed masses. Dust absorbs ultraviolet and visible light from young stars and re-emits it in the infrared, potentially affecting both photometric redshift estimates and stellar mass calculations. Better dust models might revise some mass estimates downward. Others expect that better spectroscopic measurements will reveal that some photometric redshift estimates were incorrect, moving some apparently impossible galaxies to more reasonable distances, where their properties no longer conflict with theory. But many astronomers believe the observations represent genuine challenges that will require serious modifications to our understanding of galaxy formation. The James Webb data might be telling us that gas converted to stars far more efficiently in the early universe than current models predict, that dark matter clustered differently in the first billion years than it does today, or that feedback processes from the first stars and black holes operated differently than we think. Resolving these questions will require new simulations that explore broader ranges of physical parameters and new theoretical work that considers processes we might have overlooked in previous models. The broader implications extend beyond just the technical details of galaxy formation. If the universe can produce massive evolved galaxies in just 300 million years, this suggests that the pathway from simple initial conditions to complex structures can proceed far more rapidly than we believed. This might have implications for understanding the emergence of complexity in other contexts, from the formation of planetary systems to the origin of life itself. If self-organization and structure formation can happen quickly when conditions are right, this might suggest that the universe is far more efficient at creating complexity than pessimistic estimates have suggested. The James Webb discoveries also highlight how much we still do not know about the universe. Despite a century of modern cosmology and decades of detailed observations, we are still discovering fundamental surprises about how galaxies form and evolve. We are still finding objects that do not fit into our theoretical frameworks. We are still revising our understanding of cosmic history based on new observations. This continuing process of discovery and revision represents the essence of the scientific method, the iterative refinement of models as new data becomes available. But it also reminds us of the provisional nature of scientific knowledge and the need for humility when making claims about ultimate truths. The universe proves endlessly inventive, producing phenomena we never imagined, and challenges to our understanding that push science forward. The massive galaxies appearing impossibly early in cosmic time join a long list of astronomical surprises that forced revision of established theories. Each surprise initially appeared as an anomaly or exception to the rules, but ultimately revealed deeper truths about how nature operates. Perhaps the lesson is that we should expect surprises when we venture into truly new observational territory. The James Webb Space Telescope has opened a new window on the universe, allowing us to see epochs and objects we could not observe before. Finding unexpected phenomena in this previously hidden realm might simply reflect the universe's fundamental complexity and diversity. The specific question of whether Glass E13 and similar massive early galaxies represent fatal challenges to our cosmological models, or merely surprising but explicable phenomena, will be answered through careful scientific work over the coming years. But regardless of the resolution, the discoveries have already achieved something important. They have reminded us that our models, no matter how successful or well-tested, remain provisional descriptions of reality, always subject to revision when confronted with new observations. They have demonstrated the power of advanced technology to reveal aspects of the universe we could not access before. And they have renewed our sense of wonder at the cosmos and our desire to understand its mysteries. The choice before us is not whether to accept or reject James Webb's observations. The data exists and must be explained. The choice is how to respond to this challenge, with creativity and openness to new ideas, with rigorous analysis and careful skepticism, with collaboration across research groups and theoretical frameworks, and with patience as the scientific process works to separate robust findings from artifacts. The history of science suggests that this approach, combining boldness in exploring new ideas with caution in evaluating evidence, offers the best path toward genuine understanding. The James Webb Space Telescope will continue observing for years or decades to come, each observation adding to our knowledge and potentially revealing new surprises. The massive early galaxies that challenge our current models might prove to be exceptional cases that can be explained within existing frameworks, or they might represent the first hints of a more profound revision to our understanding of cosmic evolution. Only time and continued investigation will tell. But the process of grappling with these observations, testing hypotheses, and refining our models will advance astronomy regardless of the specific outcome. We stand at a remarkable moment in human understanding of the cosmos. We have built instruments capable of observing the universe across almost its entire history, from the present day back to within a few 100 million years of the Big Bang. We have developed theoretical frameworks that connect observations of the cosmic microwave background, the large-scale structure of the universe, the abundances of elements, and the properties of galaxies into a coherent picture of cosmic evolution. And we have discovered that this picture, despite its successes, remains incomplete and must be revised as new observations reveal unexpected phenomena. The universe awaits our continued investigation. Each observation from James Webb provides another piece of the cosmic puzzle. Each analysis refines our understanding of galaxy formation, chemical evolution, and the emergence of structure from the Big Bang. Each comparison between observation and theory reveals where our models succeed and where they fail, guiding the development of improved frameworks that better describe reality. This iterative process of observation, modeling, comparison, and revision represents the core of scientific progress. The deep time perspective reveals our investigations as part of a larger story. The universe's gradual awakening to self-awareness through the emergence of conscious beings capable of observing and understanding their cosmic origins. We are the universe studying itself, using telescopes and theories to probe the past and decipher the physical laws that shaped cosmic evolution. The James Webb discoveries, whatever their ultimate implications, advance this grand project of cosmic self-understanding. They challenge our assumptions, reveal new phenomena, and push the boundaries of knowledge outward into previously inaccessible realms of space and time. The evidence surrounding us tells a story more complex and surprising than we imagined. Galaxies appeared earlier and evolved faster than theoretical models predicted. Structure formation proceeded through mechanisms we do not yet fully understand. The conversion of gas into stars and the chemical enrichment of the universe followed pathways that challenge our assumptions about these processes. These discoveries do not invalidate the scientific method or undermine the remarkable progress astronomy has achieved. Instead, they illustrate science's strength, the willingness to revise understanding when observations demand it. The James Webb Space Telescope's observations force us to confront profound questions about cosmic history, the formation of structure, and the completeness of our theoretical frameworks. We do not yet know whether resolving these questions will require minor adjustments to existing models or fundamental revisions to our understanding of cosmology and galaxy formation. But the process of grappling with these observations, testing hypotheses, and developing new insights will advance astronomy regardless of the specific resolution. Our predecessors built the theoretical foundations and observational capabilities that made James Webb possible. They developed general relativity, quantum mechanics, nuclear physics, and the Big Bang model. They launched space telescopes, built large ground-based observatories, and created the computational tools necessary for analyzing complex astronomical data. Each generation contributed to the accumulated knowledge we now possess. Our generation inherits this legacy and the responsibility to extend it by addressing the challenges that James Webb's observations present. The future remains unwritten, but the tools for investigating it grow ever more powerful. Beyond James Webb, next-generation telescopes on the ground and in space will probe even deeper into cosmic time and observe with even greater sensitivity. New theoretical frameworks will emerge from the creative work of researchers grappling with current observations. New computational capabilities will enable more sophisticated simulations of galaxy formation and cosmic evolution. The combination of advancing technology, expanding observations, and developing theory will continue pushing the frontiers of knowledge outward. The universe is vast, ancient, and complex beyond our current comprehension, but it obeys physical laws we can discover through observation and reason. It produces phenomena we can detect with the instruments of our own design. It reveals its secrets to patient investigation and careful analysis. The James Webb observations, with all their puzzles and challenges, demonstrate that we still have much to learn, but that the tools and methods for learning it continue to advance. The choice is ours, to embrace the challenges these discoveries present, to pursue understanding with rigor and creativity, and to remain open to revising even our most fundamental assumptions when the evidence demands it. The cosmos awaits our continued investigation. Deep time stretches before us, filled with mysteries waiting to be unraveled. The James Webb Space Telescope has provided a new window on this deep time, revealing phenomena that challenge our understanding and inspire our wonder. What we learn from these observations will shape astronomy for decades to come and will contribute to humanity's eternal quest to understand our place in the universe. The evidence is clear. The universe is more complex, more surprising, and more wonderful than we imagined. The massive early galaxies challenge our theories but also push science forward, forcing us to think more deeply about cosmic evolution and question assumptions we took for granted. Whether these observations ultimately lead to revolutionary changes in cosmology or to refinements of existing models, the process of addressing them advances our knowledge and demonstrates science's power to confront anomalies and pursue truth wherever the evidence leads. The James Webb Space Telescope stands as a testament to human curiosity and ingenuity, our desire to understand the cosmos, and our ability to build instruments that reveal its secrets. The discoveries it makes, including the puzzling massive early galaxies that challenge our models, continue a tradition of exploration that extends back through centuries of astronomical observation. We are privileged to live in an era when such powerful tools extend our vision across vast expanses of space and time, revealing the universe in unprecedented detail. The journey continues. Each observation adds to our knowledge. Each puzzle drives new investigations. Each surprise reminds us of how much remains to be discovered. The universe beckons us forward into deeper understanding, and we respond with increasingly sophisticated instruments, theories, and analyses. The massive early galaxies that James Webb has revealed represent just the beginning of what promises to be a transformative era in astronomy, an era when we finally observe the earliest stages of galaxy formation and confront the full complexity of cosmic evolution. The choice before humanity is clear. We can embrace these discoveries and the challenges they present, pursuing understanding with rigor and creativity, or we can retreat into comfortable assumptions that fail to account for what we observe. Science has always chosen the former path, accepting that genuine understanding requires confronting uncomfortable truths and revising cherished theories when evidence demands it. The James Webb observations continue this tradition, challenging us to think more deeply about the cosmos and our place within it. The universe is speaking to us through these observations, revealing aspects of cosmic history we have never seen before. Whether we have the wisdom to listen, the creativity to develop new frameworks for understanding what we observe, and the humility to revise our theories when they prove inadequate will determine whether this era becomes a turning point in our understanding of the cosmos or merely a collection of puzzles we fail to solve. The evidence is in our hands, the tools are at our disposal, the questions await our investigation, the universe is watching, deep time is calling, the choice is ours. The scientific response to these discoveries reveals deep divisions within the astronomical community about how to interpret such fundamental challenges to established theory. At a conference in Baltimore in November 2022, dedicated to early James Webb results, astronomers presented sharply contrasting views. Some researchers argued that the massive early galaxies represent measurement errors or misinterpretations rather than genuine challenges to cosmology. They pointed to the preliminary nature of photometric redshift estimates and suggested that follow-up spectroscopy would likely revise many claimed detections downward to more reasonable redshifts. Dr. Stephen Finkelstein from the University of Texas, a leading expert on high redshift galaxies, cautioned against premature conclusions. His team's analysis of several galaxy candidates suggested that dust extinction might be mimicking the spectral signatures of extreme distance in some cases. Dust grains in galaxies absorb blue and ultraviolet light while allowing red and infrared light to pass through, creating a spectral shape that can resemble a highly redshifted galaxy. Distinguishing between genuine high redshift galaxies and dusty lower redshift galaxies requires careful analysis of multiple spectral features, work that takes time as spectroscopic observations accumulate. Finkelstein emphasized that science requires patience and that extraordinary claims demand extraordinary evidence. But other researchers pushed back against this conservative interpretation. Pascal Esch from the University of Geneva, whose team discovered several of the most distant galaxy candidates, argued that the pattern of observations across multiple independent surveys and multiple analysis methods suggests the findings are robust. His team has obtained spectroscopic confirmation for several galaxies at redshifts exceeding Z equals 10, eliminating concerns about photometric redshift errors for those specific objects. The spectroscopic data shows clear detections of emission lines at precisely the wavelengths expected for galaxies at these extreme distances. These are not ambiguous detections that could be explained by alternative interpretations. They are definitive measurements that place galaxies unambiguously in the first 500 million years after the Big Bang. Dr. Emma Curtis Lake from the University of Hertfordshire, who led the spectroscopic confirmation of glass Z13, described the moment when her team first saw the spectrum. The data showed a clear Lyman alpha emission line at 1713 nanometers, exactly where it should appear for a galaxy at redshift Z equals 13.1. Additional emission lines from oxygen and carbon appeared at the expected wavelengths, confirming the distance and revealing the galaxy's chemical composition. There was no ambiguity in the data. This galaxy exists at the claimed distance, possesses the claimed mass, and shows the chemical enrichment that theoretical models say should be impossible at such early times. The observation forces a choice: either revise our understanding of galaxy formation or question the cosmological framework itself. The debate intensified when Dr. Michael Boylan-Colchin from the University of Texas published a theoretical analysis showing that the observed abundance of massive early galaxies exceeds lambda CDM predictions by factors of 10 to 100. His calculations, based on standard assumptions about how dark matter halos form and how gas converts into stars, demonstrate that producing even one galaxy, like glass Z 13 by redshift Z equals 13, requires extraordinary luck or extraordinary physics. Producing the dozen or more candidates observed in relatively small survey areas suggests systematic deviations from theoretical expectations. Boylan-Colchin's work sparked intense discussion about whether the problem lies with our models of star formation, our understanding of dark matter, or our cosmological framework. Some theorists proposed that the solution might involve higher star formation efficiency in the early universe. Dr. Avishai Dekh from the Hebrew University of Jerusalem developed models suggesting that cold gas streams flowing into early dark matter halos might have triggered extremely efficient star formation, converting up to 30 or 40% of infalling gas into stars, rather than the few percent typical today. These cold streams, predicted by simulations of structure formation, represent narrow filaments of gas that penetrate deep into dark matter halos without shocking and heating. Once inside the halo, the cold gas can collapse directly into stars without the usual delays associated with cooling from high temperatures. If such streams were common in the early universe, they might explain the rapid stellar mass buildup in early galaxies. But critics pointed out that even 30 to 40% star formation efficiency falls short of what is needed to explain the most massive early galaxies. Glass Z13 requires essentially all its available baryons to have converted into stars by 300 million years after the Big Bang, an efficiency approaching 100% that seems physically implausible given the various feedback processes that should prevent such complete conversion. Stellar winds, radiation pressure, and supernova explosions should blow away or heat substantial fractions of the gas before it can form stars. Achieving near-complete conversion requires suppressing all these feedback processes, but doing so contradicts our understanding of stellar physics and observed properties of star-forming regions in the modern universe. Other researchers explored whether modifications to dark matter physics might resolve the tension. Dr. Mark Vogelsberger from MIT investigated whether dark matter that interacts with itself through forces beyond gravity could accelerate structure formation in the early universe. Self-interacting dark matter experiences additional forces when dark matter particles pass near each other, analogous to how atoms interact through electromagnetic forces. These interactions could enhance the collapse of dark matter halos in the early universe, creating deeper gravitational potential wells that attract more ordinary matter and trigger earlier star formation. Vogelsberger's simulations showed that self-interacting dark matter, with carefully chosen interaction strengths, could produce more massive early galaxies than standard cold dark matter models. However, the same modifications that help explain massive early galaxies create problems for the modern universe. Self-interacting dark matter affects galaxy structure at all cosmic epochs, not just the early universe. Observations of galaxy clusters, dwarf galaxies, and dark matter substructure in the Milky Way all constrain how strongly dark matter can interact with itself. These constraints limit the interaction strength to values too small to significantly affect early galaxy formation. Finding a dark matter model that helps with early galaxies without contradicting observations of the modern universe proves extremely challenging. Most proposed modifications either fail to produce enough early massive galaxies or produce unwanted effects on later structure. The possibility of modifications to cosmology itself generated considerable discussion. Dr. Mark Kamionkowski from Johns Hopkins University explored whether changes to the early expansion history of the universe might provide additional time for galaxy formation. If the expansion rate was slower in the first billion years than lambda CDM predicts, more time would have been available for structure to form at a given redshift. Kamionkowski investigated scenarios where dark energy behaved differently in the early universe, perhaps transitioning from one form to another during the first billion years. Such transitions could temporarily slow the expansion, providing the extra time needed for massive galaxies to form. But modifying the expansion history affects many other observable quantities beyond just galaxy formation timescales. The cosmic microwave background encodes information about the universe's expansion history through its detailed temperature patterns. The positions and heights of acoustic peaks in the cosmic microwave background power spectrum depend sensitively on how fast the universe expanded during the first 380,000 years. Changing the expansion history to solve the massive early galaxy problem, while maintaining agreement with cosmic microwave background observations, requires extremely fine-tuned modifications that seem contrived rather than natural. Most attempts to modify cosmology in ways that help with early galaxies end up breaking agreement with cosmic microwave background observations or other well-established cosmological tests. A particularly intriguing possibility involves primordial black holes. Dr. Bernard Carr from Queen Mary University of London proposed that if a substantial fraction of dark matter consists of black holes formed in the very early universe, these primordial black holes could serve as seeds for early galaxy formation. Black holes created in the first second after the Big Bang could have masses ranging from microscopic to thousands of solar masses depending on when and how they formed. If a population of 1,000 solar mass primordial black holes existed, they could provide the gravitational seeds around which the first galaxies formed. These black hole seeds would eliminate the need for galaxies to grow from tiny initial perturbations, providing a head start that might explain early massive galaxies. But primordial black holes face their own observational constraints. Various searches for primordial black holes through gravitational lensing effects, their contribution to dark matter, and their potential merger signatures in gravitational wave observations have placed tight limits on how abundant they can be at different mass ranges. Current constraints largely rule out primordial black holes as the dominant form of dark matter, except in narrow mass windows that would not help with early galaxy formation. Making primordial black holes a viable solution to the massive early galaxy problem requires either that current constraints have missed a crucial mass range, or that primordial black holes contribute only a small fraction of dark matter, but were preferentially located in regions that would become early galaxies. The discussion of alternative theories revealed a fundamental tension in how science responds to anomalous observations. Conservative researchers argued for exhausting all possibilities within the existing framework before considering radical alternatives. They pointed to the extraordinary success of lambda CDM across many independent tests and cautioned against abandoning a successful theory based on preliminary observations from a new instrument. History shows that many apparent anomalies turned out to result from measurement errors, systematic biases, or incomplete analysis rather than fundamental problems with theoretical frameworks. The conservative approach prioritizes preserving theoretical frameworks that have proven successful across many domains, while working to explain apparent anomalies within those frameworks. Reformist researchers countered that genuine scientific progress requires openness to revising even well-established theories when observations demand it. They noted that every major advance in physics came from taking observations seriously even when they contradicted prevailing theories. The discovery of the accelerating universe contradicted the then prevailing belief that cosmic expansion should be slowing. Rather than dismissing the supernova observations as erroneous, cosmologists introduced dark energy and revised the cosmological model. Similarly, the massive early galaxy observations might be telling us that something important is missing from our current framework, whether in galaxy formation theory, dark matter physics, or cosmology itself. The tension between these approaches reflects broader questions about scientific methodology and the philosophy of science. How much confirming evidence does a theory need to be considered established? How much contradictory evidence justifies abandoning or revising that theory? What role should considerations of theoretical elegance or simplicity play when choosing between alternative explanations? These questions lack simple answers, and different researchers weigh the various considerations differently based on their experience, training, and philosophical inclinations. The massive early galaxy problem also intersects with ongoing debates about the Hubble constant tension. Different methods of measuring the universe's current expansion rate yield results that disagree by about 10%, well beyond measurement uncertainties. Measurements based on the cosmic microwave background and the lambda CDM model predict a Hubble constant around 67 kilometers per second per megaparsec. Measurements based on observations of nearby supernovae and other distance indicators yield values around 73 kilometers per second per megaparsec. This discrepancy has persisted despite years of effort to resolve it, suggesting either systematic errors affecting one or both measurement methods or genuine problems with lambda CDM. Some researchers have suggested that the Hubble tension and the massive early galaxy problem might share a common solution. Both problems could potentially be addressed by modifications to the universe's expansion history. If the universe expanded differently than lambda CDM predicts, this could alter both the relationship between cosmic microwave background observations and the Hubble constant and the relationship between redshift and cosmic age. Finding modifications that resolve both problems simultaneously, while maintaining agreement with all other cosmological observations, would provide strong support for revising the standard model. But so far, no proposed modification successfully addresses both issues without creating new problems elsewhere. The implications for our understanding of cosmic habitability and the potential for life in the universe add another dimension to the massive early galaxy debate. If galaxies formed and evolved rapidly in the early universe, and if chemical enrichment proceeded faster than previously thought, then Earth-like planets might have formed much earlier than we expected. The earliest stars in the Milky Way, found in the galactic halo and some globular clusters, have ages approaching 13 billion years, forming roughly 800 million years after the Big Bang. These stars have very low heavy element abundances, containing only about 0.1 to 1% of the Sun's iron and oxygen content. Such low metallicities make planet formation difficult, because planets require substantial quantities of heavy elements to form. But if some early galaxies achieved heavy element abundances approaching 20 to 30% of solar values by 400 million years after the Big Bang, as James Webb observations suggest, then planet formation might have begun far earlier than previously thought possible. Rocky planets like Earth require substantial amounts of silicon, magnesium, iron, and oxygen in the primordial disk from which they form. The Sun's chemical composition, with roughly 2% of its mass in elements heavier than helium, provides sufficient heavy elements for planet formation. If early galaxies reached similar or even higher metallicities by just 400 to 500 million years after the Big Bang, planetary systems could have formed when the universe was less than 1 billion years old. This early planet formation would have profound implications for the search for life. Life on Earth appeared relatively quickly once conditions became favourable, with fossil evidence suggesting life existed by at least 3.5 billion years ago, and possibly as early as 4 billion years ago, just 500 to 600 million years after Earth formed. If life can emerge on similarly rapid timescales elsewhere, and if habitable planets formed when the universe was 1 to 2 billion years old, then life might have existed for 11 to 12 billion years, far longer than life on Earth has existed. Any such life would have had billions of years more time to evolve and develop complexity than life on Earth. The possibility of ancient alien civilizations has long fascinated both scientists and the public. If technological civilizations emerged on planets formed when the universe was 2 or 3 billion years old, such civilizations could now be 10 billion years old, roughly twice the age of Earth itself. What might a technological civilization achieve given 10 billion years to develop? Could they have spread throughout their galaxy or even beyond? Could they have developed technologies so advanced as to be unrecognizable to us? The Fermi paradox, which asks why we have not detected signs of alien civilizations despite the seeming likelihood of their existence, becomes even more puzzling if habitable conditions emerge far earlier than we thought. One resolution to the Fermi paradox suggests that technological civilizations might be short-lived, self-destructing through nuclear war, environmental catastrophe, or other disasters before developing the capability to spread beyond their home planet. If civilization lifetimes typically measure in centuries or millennia, rather than millions or billions of years, then even if many civilizations arose over cosmic history, few or none might exist in our galaxy right now for us to detect. The James Webb discoveries do not change this possibility, but do suggest that many more civilizations might have arisen and fallen throughout cosmic history than we previously estimated. Another resolution proposes that interstellar travel is far more difficult than science fiction suggests, and civilizations remain confined to their home star systems even given billions of years to develop. The vast distances between stars, the enormous energy requirements for interstellar travel, and the challenges of keeping travelers alive during journeys lasting thousands of years might prove insurmountable barriers to expansion. If this barrier exists, each technological civilization remains isolated on its home world, preventing the kind of galactic colonization that some have predicted. In this scenario, many civilizations might exist in our galaxy simultaneously, without any of them being aware of the others due to the difficulties of interstellar communication and travel. A more speculative possibility suggests that advanced civilizations might transcend physical existence entirely, uploading consciousness into computational substrates or discovering physics beyond our current understanding that allows escape from conventional space-time. Such post-biological civilizations might be invisible to our current detection methods, existing in states or dimensions we cannot perceive. While highly speculative, this idea illustrates the challenge of predicting what billions of years of technological development might achieve. Our own civilization has progressed from the first computers to artificial intelligence in less than a century. Extrapolating such progress over billions of years ventures into realms where conventional thinking about civilization development might not apply. The massive early galaxy observations also have implications for the ultimate fate of the universe and the very long-term future. Cosmological observations indicate that the universe's expansion is accelerating, driven by dark energy. If this acceleration continues indefinitely, galaxies outside our local group will eventually recede beyond our cosmic horizon, disappearing from view as space between them and us expands faster than light can travel. In roughly 100 billion years, the Milky Way and its neighbouring galaxies will find themselves alone in an observable universe, with all other galaxies having receded beyond detection. The cosmic microwave background will have redshifted to undetectable wavelengths. Future astronomers in this distant epoch will face a universe that appears to contain only their local group, with no evidence of the Big Bang or cosmic expansion. But if the early universe was more efficient at forming galaxies than we thought, this efficiency might extend to other aspects of cosmic evolution. Perhaps stars form more efficiently from interstellar gas, depleting galactic gas reservoirs faster than current models predict. Perhaps stellar evolution proceeds differently in subtle ways that affect long-term galactic evolution. Understanding these early efficiency differences might help us better predict the long-term evolution of galaxies and the ultimate fate of star formation in the universe. Current models predict that star formation will continue in galaxies for trillions of years, gradually declining as gas reservoirs deplete but never completely ceasing. If early universe observations force revisions to these models, the timeline for long-term galactic evolution might change. The philosophical implications of these discoveries extend beyond scientific details to questions about the nature of knowledge itself. The James Webb observations challenge our confidence in theories we thought were well established, reminding us that scientific knowledge remains always provisional, always subject to revision when new observations demand it. This provisionality is not a weakness of science, but rather its greatest strength. Science advances by questioning even its most cherished theories and demanding that theories match observations rather than the reverse. The willingness to revise understanding when evidence demands it distinguishes science from dogma. Yet this provisionality can create confusion when communicated to the public. News headlines announcing revolutionary discoveries one year, followed by retractions or major revisions the next, can create the impression that scientists don't know what they're doing or that scientific knowledge is unreliable. But this impression misunderstands the scientific process. Science proceeds through cycles of observation, hypothesis, testing and revision. Early results from new instruments or techniques often require refinement as analysis methods improve and more data accumulates. This iterative process eventually converges on accurate understanding, but the convergence takes time and involves intermediate steps where understanding remains incomplete. The James Webb massive early galaxy situation exemplifies these challenges. Early photometric redshift estimates suggested numerous galaxies at redshifts exceeding Z equals 12 or even Z equals 15. Follow-up spectroscopy has confirmed some of these distances while revising others downward. The picture will likely continue evolving as more observations accumulate and analysis techniques improve. Eventually, we will know with confidence which early massive galaxies are real and which were misidentifications. But reaching that point requires patience and careful work that does not always align with the rapid pace of modern science communication. The discoveries also highlight the crucial role of technological development in driving scientific progress. Every major advance in astronomy has followed the development of new observational capabilities. Galileo's telescope revealed moons orbiting Jupiter and phases of Venus, providing crucial evidence for the heliocentric model. Larger telescopes in the 18th and 19th centuries resolved distant nebulae into galaxies, revealing the universe's vast scale. Radio telescopes discovered pulsars, quasars, and the cosmic microwave background, opening entire new windows on cosmic phenomena. The Hubble Space Telescope's sharp images revolutionized our understanding of galaxy evolution and cosmic expansion. James Webb continues this tradition, pushing our observational reach to unprecedented distances and sensitivities, but it will not be the last revolutionary instrument. Plans are already underway for next-generation ground and space telescopes that will surpass even James Webb's capabilities. The Giant Magellan Telescope, with its 25-meter primary mirror, will achieve spectroscopic sensitivities far exceeding current instruments. The Extremely Large Telescope in Chile will have a 39-meter primary mirror, the largest optical telescope ever built. These ground-based behemoths will complement James Webb's space-based observations, providing different capabilities and perspectives on the high redshift universe. Future space missions might deploy even larger infrared telescopes or use novel techniques like interferometry to achieve extraordinary angular resolution. Interferometry combines light from multiple separate telescopes, achieving a resolution equivalent to a single telescope with diameter equal to the separation between the telescopes. Space-based interferometers could achieve angular resolutions thousands of times better than James Webb, potentially resolving individual star-forming regions in galaxies at redshift z equals 10 or beyond. Such capabilities would transform our understanding of early galaxy structure and evolution, revealing physical processes operating on scales far too small for current instruments to observe. James Webb continues this tradition, pushing our observational reach to unprecedented distances and sensitivities, but it will not be the last revolutionary instrument. Plans are already underway for next-generation ground and space telescopes that will surpass even James Webb's capabilities. The Giant Magellan Telescope, with its 25-meter primary mirror, will achieve spectroscopic sensitivities far exceeding current instruments. The Extremely Large Telescope in Chile will have a 39-meter primary mirror, the largest optical telescope ever built. These ground-based behemoths will complement James Webb's space-based observations, providing different capabilities and perspectives on the high redshift universe. Future space missions might deploy even larger infrared telescopes or use novel techniques like interferometry to achieve extraordinary angular resolution. Interferometry combines light from multiple separate telescopes, achieving a resolution equivalent to a single telescope with diameter equal to the separation between the telescopes. Space-based interferometers could achieve angular resolutions thousands of times better than James Webb, potentially resolving individual star-forming regions in galaxies at redshift z equals 10 or beyond. Such capabilities would transform our understanding of early galaxy structure and evolution, revealing physical processes operating on scales far too small for current instruments to observe. These future capabilities will test and extend whatever new understanding emerges from James Webb observations. If theorists develop revised models of early galaxy formation to explain the massive early galaxies, future instruments will test those models in unprecedented detail. If cosmologists propose modifications to lambda CDM, new observations will either confirm or refute those modifications. The cycle of observations spurring theoretical development, spurring new observations continues, driving astronomy forward even as each answer raises new questions. Consider what remains to be understood. We do not fully know how the first stars formed or what their properties were. We do not understand in detail how supermassive black holes grew so rapidly in the early universe, or how they came to dominate galaxy centers. We do not know whether galaxy formation proceeded smoothly or through discrete stages marked by violent events. We do not know whether the universe underwent any phase transitions between the Big Bang and the present that might have affected structure evolution. We do not know how common or rare life is in the universe, or whether technological civilizations typically survive long enough to spread beyond their home worlds. The James Webb observations provide new constraints on these questions, but also reveal how much we still have to learn. Each answer raises new questions. Each solved mystery reveals deeper puzzles. This pattern has characterized astronomy throughout its history. When Galileo first turned his telescope skyward, he discovered craters on the Moon, spots on the Sun, phases of Venus, and moons orbiting Jupiter. These discoveries answered some questions but raised countless more about planetary bodies, celestial mechanics, and the structure of the solar system. 4 centuries of investigation have answered many questions but revealed ever more profound mysteries about cosmic evolution, dark matter and dark energy, and the ultimate origin and fate of the universe. The James Webb massive early galaxy discoveries fit this pattern. Whether they represent minor puzzles that will be resolved within current frameworks or harbingers of revolutionary new understanding, they demonstrate that the universe retains the capacity to surprise us. The cosmos is far more complex, dynamic, and fascinating than we imagined. Our current understanding, despite a century of modern cosmology and remarkable observational and theoretical achievements, remains incomplete. Future astronomers will likely look back on our current puzzlement about massive early galaxies with the same perspective we now have on earlier mysteries that seemed intractable until the right observations or theoretical insights resolved them. The universe is patient. It has existed for 13.8 billion years and will persist for trillions more. The answers to our questions about massive early galaxies, galaxy formation, and cosmology exist, waiting to be discovered through continued observation and theoretical work. Whether those answers come through refinements to existing models or revolutionary new frameworks, the process of finding them will advance our understanding and reveal new aspects of cosmic reality we have not yet imagined. The choice before us is clear. We can embrace the challenge these observations present, pursuing understanding with the full resources of modern astronomy and theoretical physics, or we can retreat into comfortable assumptions that fail to account for what we observe. Science has always chosen the former path, advancing through cycles of observation, theoretical development, testing and revision. The James Webb observations continue this tradition, challenging us to think deeply about the cosmos and our ability to understand it. The universe speaks to us through telescopes and theories. The message is still being decoded, but its existence is undeniable. Massive galaxies appeared earlier than we expected. Structure formed more rapidly than our models predicted. The conversion of gas to stars proceeded more efficiently than we understood. These observations demand explanation, and finding that explanation will advance astronomy regardless of whether it comes from refinements to existing models or revolutionary new frameworks. the cosmos beckons us forward into deeper understanding. The tools at our disposal grow ever more powerful. The questions before us grow ever more profound. We stand at a remarkable moment in the history of astronomy, when our most advanced space telescope reveals phenomena that challenge our most fundamental theories. How we respond to this challenge will determine whether this era marks a turning point in our understanding of cosmic evolution or merely another step in the ongoing process of refining our knowledge. The James Webb Space Telescope has given us a new window on cosmic dawn, revealing a universe more complex and surprising than we imagined. Whether that complexity requires minor adjustments to existing theories or fundamental revisions to our cosmological framework, the discoveries push astronomy forward and deepen our understanding of how the universe evolved from the Big Bang to the rich diversity of structures we observe today. The journey of discovery continues, driven by human curiosity and enabled by ever more powerful tools for probing the cosmos. We are privileged to witness this era of discovery, when instruments of remarkable sophistication reveal phenomena that challenge our deepest theories about cosmic origins and evolution. The massive early galaxies that James Webb has found represent more than just astronomical curiosities. They embody the ongoing dialogue between observation and theory that drives scientific progress. They remind us that the universe retains mysteries that current understanding cannot explain. They challenge us to think more deeply, observe more carefully, and remain open to revising even our most cherished theoretical frameworks when evidence demands it. The cosmos beckons, the mysteries await, the tools stand ready. The universe is speaking to us through the light of distant galaxies, telling us that our current understanding remains incomplete. Whether we have the wisdom to listen, the creativity to develop new frameworks for understanding what we observe, and the humility to revise our theories when necessary will determine how this chapter of cosmic exploration unfolds. The evidence is in our hands, the questions await investigation, the universe is watching, deep time is calling, the choice as always is ours.